Welcome to Unit 11, Part 2. In this part, we're going to work a couple of examples involving conservation of energy. For our first example, we are going to look at a hanging mass on spring. So here we have a spring. We're given the spring constant of 53 newtons per meter. It's hanging next to a ruler. We're told that the end of the spring is next to the 15 centimeter mark, and then a 2.5 kilogram mass is attached and it goes down, and we want to know where does it end up next to the ruler. Okay, so here is the setup for this problem. We have the spring. This is that originally 15 centimeter mark, but for the moment, that doesn't matter. We'll bring that in at the end. We then add a mass to it, and that spring, it's the same spring, but I'm going to draw it again, stretches out, and we are told that this is that 2.5 kilogram mass. Right. So we're going to let it have stretched a distance of h. At neither point is the mass, or the spring, if you will, moving. The first point is just hanging still and nothing's going on. The second one, it moved obviously to get down there, but it's now at rest again. So if we think about energy, this first spot, we have no elastic potential energy because the spring is unstretched. We do, however, have gravitational potential energy equal to mgh. At the other end, or other spot, if you will, our spring is now stretched. So we have elastic potential energy. Remember, the formula for that is 1/2 kx squared, but the distance it's stretched in this case is h, so I'm going to plug that in, 1/2 kh squared. But we have no final gravitational potential energy because we can consider this to be h equals 0. Okay, now conservation of energy tells us that our initial energy has to equal our final energy. So that's our not KE. There is no KE in this problem. Let's try again. EPE initial plus GPE initial has to equal EPE final plus GPE final. Well, EPE initial was 0 plus our GPE initial, which we found to be mgh. EPE final is 1/2 kh squared, and our GPE final is 0. We see the two zeros, so we don't really need to consider those because adding 0 doesn't do anything. So 1/2 kh squared. We have a factor of h on both sides of the equation, therefore we can cancel one of them. And we can now solve for h equals 2mg divided by k. So that's 2 times the mass, which was 2.5 kilograms, times g, which is 9.8 meters per second squared, divided by the spring constant, which is 53 newtons per meter. And if you put all of that in, you get h equals 0.92 meters. Or in other words, 92 centimeters. But that 92 centimeters is measured from our 15 centimeter mark. So if this is 15, then this spot down here has to be 15 plus 92 centimeters, or in other words, 107 centimeters. So the answer to the question is, where will the spring line up with the ruler marks? It will line up with the 107 centimeter mark, meaning that this had better be a 2 meter ruler and not a 1 meter ruler. For our next example, we're going to think about a gravitational potential energy example. So in this example, we have the floor. We have a cart. I put it on wheels so it looks like a cart. On top of the cart, there is a book, and we are told that the cart is 1 meter high, and above the cart, at the 1.5 meter mark, there is a shelf, and we are told the mass of the book is 0.5 kilograms. We want to know how much gravitational potential energy is gained. What is the change in gravitational potential energy to move the cart move the book from the cart to the shelf? Okay, well, I'm going to continue with what I have here. I'm going to let this be h equal 1 meter, this be an h equal 1.5 meter, and make the floor h equals 0. So at our initial height, GPE initial, we have m, which is 0.5 kilograms, times g, which is 9.8 meters per second squared, times h, which is 1 meter. And if you put all of that into a calculator, 0.5 times 9.8 times 1, I'm having calculator errors. There we go. You get that this is 4.9 joules of initial gravitational potential energy. And when the book is on the shelf, you get 0.5 kilograms times 9.8 meters per second squared times 1.5 meters. And you get 7.35 joules of energy. So now we can find the change in gravitational potential energy is the final gravitational potential energy minus the initial gravitational potential energy, 7.35 joules minus 4.9 joules. And that equals 2.45 joules. Answer found. Now, I'm going to rework this problem slightly. So I'm still going to have my cart on its wheels. Here's my book. Here's my shelf. What really matters in this problem is not the fact that the cart is 1 meter above the floor and the shelf is a half meter above that. What really matters is that the distance between the shelf and the cart is 0.5 meters. So here my gravitational potential energy initial will be 0 joules because the height is 0. Here my gravitational potential energy will be 0.5 kilograms times 9.8 meters per second squared times 0.5 meters. And that equals 0.5 times 9.8 times 0.5, 2.45 joules. So our change in gravitational potential energy, GPE final, minus GPE initial, is 2.45 joules, which is exactly what I got on the previous slide. Okay, so this isn't really a conservation of energy problem because we are not conserving energy. We're looking at a change in gravitational potential energy. But it's an important point to get out is what matters with gravitational potential energy is not the absolute value of the gravitational potential energy. So for example, when the book is on top of the cart here, it's at 0 joules by definition because of where I put h equals 0. Here it's at 4.9 joules of energy because I put h equals 0 in a different spot. No matter where I put that h equals 0 spot, no matter where I put my gravitational potential energy equal to 0, for the same motion, I get the same change in gravitational potential energy. meaning that you are free to put your 0 for gravitational potential energy wherever is most convenient for the problem. You could even have put it as one more example because you wanted to. Cart, bookshelf. I could put H equals 0 at the shelf, which means if up is positive, this is H equals negative 0.5 meters. My GPE final will be 0 joules. My GPE initial will be 0.5 kilograms times 9.8 meters per second squared times negative 0.5 meters, which is negative 2.45 joules. Okay. But my change in GPE final minus GPE initial will be 0 joules minus negative 2.55 joules. And I still get a change in energy for this motion of 2.45 joules, regardless of where I put H equals 0. The next example is a good conservation of energy example. We're actually going to deal with all 3 types of energy possible. We have a 2 kilogram block sliding across a frictionless surface at 3 meters per second. It goes down a 20 meter tall hill and then slides across a second flat surface before impacting a spring, and I give you the spring constant. Okay, before we get into the questions, let's draw a picture so that we're all on the same page about what's going on here. So here is my block moving at, what did I say, 3 meters per second. The height of this hill is 20 meters. So remember, I am free to put my 0 for height or my 0 for gravitational potential energy wherever it is convenient. So I'm going to let the lower surface be at H equals 0 and the upper surface be at H equal 20 meters. Okay, so the block slides through, slides down the hill, comes across here, and at the very end there is a spring which is compressed. Okay. So I'm going to label this point A in the motion before it goes down the hill. Point B is after it goes down the hill but before it impacts the spring. And C is at the spring, when it's pushed the spring in as far as possible. So we have 3 questions for this problem. We want to know the block's total energy. We want to know how fast it's moving at the bottom of the hill and how far it compresses that spring. Okay, so for the first part, we want to know the block's total energy. To find the block's total energy, we look at point A. And at point A, we have 2 types of energy. It has gravitational potential energy equal to 2 kilograms times 9.8 meters per second squared times 20 meters. And that works out to be 392 joules of energy. It also has kinetic energy because it is moving, so that's 1/2 times the mass, 2 kilograms, times the square of the magnitude of the velocity, which we are told is 3 meters per second, which is 9 joules. And so E total is going to be the GPE at this point plus the KE at this point. So 392 plus 9 is 401 joules. For part 2, not KE, sorry, it wants to know how fast is it going at the bottom. Oh, I'm not writing this very well. Let's try again. V at bottom. Okay, for that, we look at point B before it has impacted the spring. The GPE at this point is 0 joules because we have defined that position to be the H equals 0 position. However, it does still have kinetic energy, which is going to be 1/2 times the mass, which is 2 kilograms, times the speed at the bottom squared, which is going to be V bottom squared, because 1/2 times 2 is 1. Energy has to be conserved, so the total energy has to equal the kinetic energy, which gives us that 401 joules equals V bottom squared. And there were units here that I've dropped, but they're kilograms, so joules divided by kilograms will give us meters squared per second squared. So the units do work out, even though they're not written very well. I guess I could do this times 1 kilogram, if you will, just to put the units back in. So V squared is going to equal 401 meters squared per second squared, and V is going to be the square root of that, which to within round off is 20 meters per second. Remember, 20 squared is actually 400, so there are some decimal places there that are not being written to make that a true statement. For the last part, at point C, this is part 3, I believe, the spring compression. Okay, so this is point C in the motion. Redrawing that a little bit, what we have is we have the block coming into the spring. Here's the spring, we can do that. So this is the initial situation. So the initial energy could be a combination of KE plus EPE, but the spring here isn't compressed yet. So EPE is 0, and the KE is 1/2 mv squared, where that V is what we found in the previous part of 20 meters per second. However, we know the answer to this. We know that this has to equal 401 joules because that's the total energy we have for this portion. The spring, or the block, hits the spring, boop, 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 and compresses it as far as possible, which means the velocity is now 0. So again, our energy could be a combination of KE, and this should be a final, KE plus EPE, but the kinetic energy is 0 in this case because it's not moving. So the energy is only 1/2 kx squared, where this x is how much the spring has compressed. Remember, by definition, that x is the change in length of the spring relative to its unstretched or uncompressed length. We can now say the initial energy here equals the final energy, so 401 joules equals 1/2 kx squared. K was 10 newtons per meter, x squared. So that means x squared equals 80.2 meters squared, which means that x is the square root of that, which is 8.96 meters. This concludes this part of Unit 11. In the next part of Unit 11, we're going to introduce a related concept, the concept of power.